Good evening everyone. My name is Devlina Maiti. I am a research scholar in the Department of Mathematics, IIT Kharagpur. And this is the 7th problem solving session of basic real analysis, and the course instructor is Professor I.K. Rana. So in this session we will discuss about function of bounded variation and Riemann integration. Okay, we'll wait for a few minutes and then we'll start. Okay, so let's start this session. So first we will discuss what is a function of bounded variation. So we'll start with functions of bounded variation. Okay, so what is a partition of a closed interval? So suppose AB is a closed interval. Now a partition P of the closed bounded interval AB is a finite ordered set that is x0, x1 and xn of points of AB such that A equals to x0, which is less than x1, less than x2 and so on, and less than xn, which is B, right? So then P is said to be a partition of this closed interval AB. So AB is this closed interval and AB is x0, this is xn, and there is some x1, x2 like this. Not equidistant, but there are in between A and B, right? Okay, so P is said to be a partition of this closed interval AB when this x0 is A and this all those xi's x1, x2, xn, they are monotonically increasing and they are in between A and B. Okay, so then P is a partition of this closed interval. Now the definition of bounded variation. So f is a function from AB to R wave function. Now denote this number VPF and P is a partition of this AB. Then VPF is denoted by this sum fx1 minus fx0 like this, and then fxn minus f of xn minus 1. Okay, this is VPF. Now if this set, now for a single partition we are determining this VPF. Okay, now we will take the whole set VPF where P belongs to this PAB. What is this PAB? PAB is the family of all the partitions of this closed interval AB. Okay, so if this set, this VPF where P belongs to this set of all family of all partitions of AB, if it is bounded above, so this set if this set okay, I will name it by say, okay, I will write it again. So if this set, this script PAB is bounded above, then f is said to be a function of bounded variation. Then f is said to be a function of bounded variation, or in short we will write f is BV. F is, I am writing this VV. for bounded variation. Okay. Now if it is bounded above, then the supremum exists, right? So then we'll denote supremum of this BPF, where all those P are taken from this script AB. We will denote it by this BABF. Okay, right? So if this is less than infinity, means if this supremum is bounded, then f is a function of bounded variation, right? Now here note that if it is 0, then what happens? BABF is 0. Then we'll see that it is 0 if and only if f is a constant function. Why? So if f is a constant function, then VAB is 0, because this VPF, this number, this VPF is going to be 0 for any partition, because f of xi is all are same. Suppose fx is k, so all of these are k, so each of this norm is 0, so VPF is 0. So this set BPF, where P belongs to for all partitions, it is 0. So this implies this supremum of this set, which is also 0. So if f is constant, if fx is equal to k for all x belongs to AB, then VPF equals to 0 for all of the partitions, right? So this means this VAB, the supremum of this set, is also 0. There is only one number. Now what happens when this is 0? VAB is 0. So for the converse, so BABF is 0. This means this supremum, this VAB is this supremum, right? So supremum is 0, and all of this term, these VPFs, are non-negative. They cannot be negative. So, and the supremum is 0. So all of the term VPF are 0, right? For any partitions it is 0, it means. So this implies VPF is 0 for all P belongs to this, all the partitions, it is 0, right? Now what is VPF? It is this sum of these differences, right? Now if we take this partition, so take the partition P0 equals to AXB, right? So this is our AB closed interval, and X is any number in between them. So this is our partition P0. So for this partition also VPF is 0. So VP0 F is 0. Now what is VP0 F? It is f of x minus fa plus f of b minus fx, right? This is 0. Now both of them are non-negative, so both are 0. So mod of fx minus fa is 0, and fb minus fx is 0, and this will implies what? This will implies fx equals to fa equals to fb, and since x is arbitrary number in between them, so fx is some constant, right? So this implies f is constant. So this BABF is 0 if and only if f is a constant function, right? Okay, now we'll see for another functions. So first we'll take the identity function. So take fx equal to x, where x belongs to ab. Now is this function a bounded variation, a function of bounded variation or not? That we will check. So for that we have to calculate BPF, right? So first take any partition P. So P equals to x0, x1 to xn be any partition so P be any partition of this AB, and this means this x0 is A and this last xn is B. Okay, now for this, what is BPF here? So it is, the formula is this one, xn minus, right? Now it is nothing but x1 minus x0 plus x2 minus x1 and this, and since x1 is bigger than x0, so this is nothing but the mod will go and it is xn minus x0, which is b minus a, right? So BPF is this set a minus b. So if we take this set, we have to find the supremum of this set for all partitions, right? And what is this set? This set is b minus a only, right? So supremum of this set is b minus a, which is finite. So this means f is a function of bounded variation, right? So supremum of this set is b minus a, which is finite. So this implies f is bv, means f is a function of bounded variation.
Ma'am, which book are you referring for these functions?
What?
Which book are you referring for these type of examples and definitions, ma'am?
Examples?
And for definitions, which book are you referring, ma'am?
I will refer Bartlett, you know the book by Bartlett
Yes, ma'am.
Sherber?
Yes, ma'am.
And you can also follow Iske Mapa. That is a very basic book and you can get everything on that book. Okay.
Can you repeat it again? Iske Mapa.
Okay, I'll write this down at the last, or okay, I'm writing this. So the book by, I think, Rudin you can also follow, but for basic this is not difficult, but I'll say you can see that on Iske Mapa is there. Okay, this is a basic real analysis. Name are same. Okay.
Yes, ma'am.
Okay, now let's see another example. So identity function is a function of bounded variation. Now take this function sin x or cos x. So is this function a function of bounded variation? In suppose AB. So is it a function of bounded variation? So first we will take P be any partition right. Now what is VPA? This is sin x1 minus sin x0 plus sin x2 minus sin x1 and sin xn minus sin xn minus 1, right. Now sine function is what? It is differentiable, right, in AB and continuous on the closed AB. So you can apply the Lagrange mean value theorem. So what is Lagrange mean value theorem? What? So Lagrange mean value theorem was if f is continuous on closed interval AB, differentiable on open AB, then what we have? Then what we have? AB minus FA equals to B minus A into F dash C, where C is a number in between A and B, right? This was the Lagrange mean value theorem. Now here our function is sin x, so we can write sin x1 minus sin x0 by x1 minus x0 into f dash c. So f dash is cos, so some cos of zeta, right, where zeta belongs to in between x0 and x1, right. So this will have for this function. So this means sin x1 minus sin x0 equals to mod of x1 minus x0 into mod of cos zeta, where zeta between x0 and x1. Now cos is also less equals to 1 modulus of this value, so this is less equal to what? X1 minus x0. Now we'll use this thing in this VPF. So using this, what will we get? We'll get VPF equals to will be less equal to x1 minus x0 plus x2 minus x1 and so on, like xn minus xn minus 1, right. And since x1 is greater than x0, so modulus will go, so this is x1 minus x0 xn minus x minus 1, and it will be also b minus a. So VPF is less equals to b minus a for any partition. So this means this set is bounded by this b minus a, right? So supremum will exist, and the supremum is also less equals to b minus a. So this means, so each of these value is less equals to b minus a. So supremum of this will be less equals to b minus a. Can be b minus a, but it will be definitely less equals to b minus a. So this means the supremum is finite, right? Cannot be infinity. So this implies f is a function of bounded variation, right? So sine function, cos function, both can be applied in this way by this mean value theorem. So they are function of bounded variation, right? Now let's look at example which is not a function of bounded variation. So if if x is rational, and 0 if x is irrational or otherwise. Okay. You will see that this function is not a function of bounded variation. So we have to find a partition which will give that the number will not be a finite number. It will goes to infinity, right? So we have to find a partition. So take this partition P equals to like this, and x to n be a partition of 0, 1 such that this x naught, the even terms x4, all of these are rationals, and the odd terms are irrationals. Okay, so you are choosing a partition in this way. The even terms are rational and the odd terms are irrational, right? So then for this partition, so since this is a particular partition, so we'll denote as P naught. So for this partition, so what is this V P naught F? So this is fx1 and so on. Right. Now see, for each of these modulus, one of them is 0 and one of them is 1, because for the first one, f of x1 is x1 is irrational, right? So for irrational number, what we have, for irrational we have fx is 0. So for fx1 is 0, right? And what is f of x naught? Since x naught is rational, so f of x naught will be 1, right? Similar for the next one. So f of x2 is rational, so it is 1, and f of x1 is irrational, so it will be 0. So in each of these modulus, one of them is 0 and one of them is 1, right? So this will be, so each of these modulus gives 1, and how many 1 is there? So we have x0 to x to n, 2n plus 1 number. So this will be 2n, right? So b p naught f is 2n. Now, so this number, this 2n depends upon n. So if we increase the points, it will go to infinity, right? So this means this goes to infinity as n goes to infinity. So this can never be bounded by some number, right? If I give you any number m, you can find a n such that 2n is bigger than this m, right? So there will be never such a m to bound it. So this implies f is not a function of bounded variation. Not PV, right? So this function is not a function of bounded variation. Okay, now we'll see a result which says if f is a function of bounded variation, then it is bounded. So it is a theorem. So f is BB, means f is a function of bounded variation, then it will imply f is bounded. Okay. So you have to prove it. So f is a function of bounded variation means the supremum of this set VPF is bounded, right? So supremum of this VPF where P varies in PAB, that is a family of all partitions of AB. So this is nothing but this ABF, BABF, and which is bounded. Less than infinity means it is bounded. So suppose it is M. So suppose M is this, we are naming it. So it is less than infinity. Now choose a point X between A and B. So P naught equals to this partition A, X and B, right? So we have to prove that f is bounded. This means we have to show that mod fx is less equals to some k for all x belongs to AB, right? So we have chosen this partition. So for this partition also, so B P naught f will be less equals to M, right? Since this is the supremum. So B P naught f is fx minus fa plus fb minus fx is less equals to M. Now sum of these two modulus is less equals to M, means each of them is less equals to M. So fx minus fa is also less equals to M, and this will give you fx is less equals to M plus mod of fa, right? So fx is bounded, right? Because M is less than infinity and this is just a number, fixed number. So this gives f is bounded. So if f is a function of bounded variation, then it is bounded. But boundedness does not imply bounded variation, because you have already seen this function, this fx in example 3 is bounded function, is bounded by 1, but it is not a function of bounded variation, right? So the converse does not hold. So converse is not true, right? Now there are some results which will give you when a function is a bounded variation function. So let f is a be a function. Okay. Now there are few conditions which will directly give you if it is a function of bounded variation or not. So the first one is, if f is monotone, then f is a function of bounded variation. And the second one is, if f is Lipschitz continuous, then also f is function of bounded variation. And the third one is, if f is continuous on AB and f dash exists, means it is differentiable and f dash is bounded, and bounded on AB, then f is a function of bounded variation. Okay. So these are some conditions to identify if a function is bounded variation or not. So the first 1 and 2 are very easy. Okay, so for 1, I'll just give a hint. So f is monotone, right? So suppose f is monotonically increasing. So suppose f is monotonically increasing, right? So we'll choose any partition P. So P is, suppose x1 to xn, be any partition belongs to this family of all partitions of AB. Now our VPF will be f of x1 minus f of x0 like this. Now since f is monotonically increasing, so x0 less than x1 means f of x1. So x0 less than x1 like this, since this is a partition. So this will imply f of x0 is less than f of x1 and less than xn, right? Since this is monotonically increasing, so since this is not strictly monotone, so there will be some equal to sign. So this means VPF will be what? So it will be, so f of x1 is greater than f of x0, so modulus will go. So only this term will remain. So this means it will be f of xn minus f of x0, which is fb minus f, right? So this is a constant term. So this means the supremum of this VPF will be fb minus fa, which is bounded. So f will be a function of bounded variation. And similarly you can prove 2. So 1 and 2 are done. And for 3, please do this 2 part on your own. Okay. So for 3, f is continuous on AB and f dash exists and bounded on AB. So here we have to use the Lagrange mean value theorem, what we have used in this sine function. Okay, similar thing. In sine function we have used the Lagrange mean value theorem. Similarly for 3, so P is any partition Xn, and then Vpf is like this, and using the Lagrange mean value theorem, so we will have f of x1 minus f of x0 is nothing but x1 minus x0 f dash some zeta 1, right, where zeta 1 lies between x0 and x1. And for the second term it will be x2 minus x1 f dash zeta 2, where this zeta 2 lies between x2 and x1. And like this, the last one will be xn minus 1 f dash zeta n, right. So where this zeta is belongs to xi minus 1 to xi, right? Yes. So and I runs from 1 to n. So Vpf now, so it is now modulus of x1 minus x0 is positive. Now modulus of f dash is bounded. We are given in 3 f dash is bounded. So this will be less equals to some k times x1 minus x0 plus x2 minus x1 and xn minus 1, right, where k is what? K is, suppose f dash x is less equals to k, because f dash is bounded, so we have taken the bound to be k. So then it is what? It is k times b minus a. So Vpf is less equals to k times b minus a for any partition, because P was an arbitrary partition. So this implies the supremum is also less equals to k into b minus a. So f is a function of bounded variation, right? Okay, so let's see one example. Okay, so what about this function? Is this, so in 0 1 if x belongs to, in 0 1, is it a function of bounded variation or not? So this f is continuous, right? Because we have already seen that x sine 1 by x is continuous. So x square sine 1 by x cos 1 by x is also continuous. So this function is continuous, and also it is differentiable because there is x square. Okay, so f is continuous on 0 1 and differentiable. Right? So what is f dash?
I'm sorry for the interruption. Can you again tell me that how in the previous example,
In
uh,
previous example,
in the last, yes,
yes.
how did we put less than or equal to k of x1 minus x0 plus and so on xn minus xn minus 1? And in the next step, we put in terms of x1 minus x0 plus x2 minus x1 plus and so on. The term was replaced by b minus a, right? No? How did we do that?
Actually, x naught is a and xn is b. So it will be cancel out. This x1 will be cancel out. All this minus term, this xn minus a will be cancel out. So the remaining will be k times xn minus x naught. And the first is x naught is actually a, and the last xn is actually b. So we are partitioning a b. So first and last has to be a and b. Okay. So xn is our b and x naught is a. So that's why k times b minus a. Now, is it clear now?
Yes,
Okay. Okay, so this f is continuous and also differentiable on 0 1. So what is f dash then? So f dash x is 2x plus sine 1 by x, right, when x belongs to 0 1, right? So what is mod of f dash x? So it will be less equals to so since x belongs to 0 to 1, so it is bounded by 2 and it is bounded by 1. So mod of f dash is bounded by 3. So we'll apply this 3 part, that if f is continuous on AB, f dash exists and it is bounded on open AB, then f is a function of bounded variation. So this imply this example 4 is a function of bounded variation. So f is function of bounded variation on 0 1, right, using the previous theorem. So using 3 from the previous exercise. Okay. Okay. So we'll see another example. So f is a function on 0 to 1 and fx is defined by x cos pi by 2x when x not equals to 0 and 0 when x equals to 0. Okay. So this function is continuous. So now is it a function of bounded variation? If you do the differentiation, then you will see that f dash is not bounded, because there will be some term 1 by x, right? So you cannot apply the previous theorem. So here f is continuous, right? Now we'll prove that this function, though it is a continuous function, it will not be a function of bounded variation, right? So continuous is not enough to say it is a function of bounded variation. So we'll choose this partition P naught to be this partition of 0 1. Okay, so for this partition P naught F will be, okay, first we'll calculate what is f of 1 by 2r. So what is f of 1 by 2r? So it is 2r times cos of right. Oh, actually it will be 1 by 2r, right? So it is 1 by 2r by, right, for r equals to 1 to n, right? So f of 1 by 2r is minus 1 to the power r by 2r, and what is f of 2r minus 1? So it is 2r minus 1 times cos of 2r minus 1 pi by 2. Right? So it is 0. So this value is 0 for r equals to 1 to n. Right? So f of 1 by 2r is this, and f of 1 by 2r minus 1 is 0. Now we will calculate v of p naught f. So this is what? This is mod of f of, so the partition was 1 by 2n 0. So 1 by 2n minus f of 0 plus f of 1 by and so on, and the last one is f of 1 minus f of half. Right? Now, so f of 1 by 2n is, and f of 0 is 0. It is given in this function, the definition of this function. So the first term will be 1 by 2n, right? And the second one will be f of 1 by 2n minus 1 is 0. So the term will come from f of 1 by 2n, which is minus 1 to the power r by 2r, that is, and there is modulus, so it will be 1 by 2n, this whole modulus, right? So the second term will be also 1 by 2n, right? And the third term, this 2n, this 1 by 2 of n minus 1 will be there, and the other will be 0, right? So for even term there is some non-zero part, and for odd term, that is odd in the denominator, right, there will be, then it will be 0. So the next will be also 2n minus 2, and so this time will become in pairs, and for the last f1, f half is half, and f1 is 0. Right? So if we sum, then it will be right, because 1 by 2n and 1 by 2n will be 1 by n, and all of this is 1 to 1 by n, right? So this is the sum. This is for V of P naught F. Now this series is divergent, means this sum goes to infinity as n goes to infinity, right? So this sum goes to infinity as n goes to infinity, means this P naught F is not bounded. It depends on n, and when n increases, it will also increase and goes to infinity, right? So this will imply f is this function, this f, though it is continuous, but it is not a function of bounded variation on 0, 1, right? Okay, I have to go fast then. Now what is a refinement of a partition? So we'll see refinement of a partition. So suppose this is a partition. So this is 0, 1, and we have taken half. Okay. So this is a partition of 0, 1, 0, half, 1. This is a partition. Now we will refine it. So if we put this number 1 by 4 here and 3 by 4 here, then this partition, this 0, 1 by 4, half, 3 by 4, 1, this is a refinement of this partition 0, half, 1. Okay. So suppose this is a partition, and then Q is also a partition of 0, 1, right? And Q is a refinement of P. So Q is a refinement because P is contained in Q. Okay. P is a proper subset of Q, right? So the definition is Q is a refinement of P if P is a proper subset of Q. Okay. Now we'll see that if VPF is there for a partition P, we can calculate VPF. Now if we define the partition P, then VPF will increase. Okay. So the theorem says maybe it will be 2. So let f be a function of bounded variation on this closed interval AB. Okay. And P be a partition of AB. So if Q is a refinement refinement of P, then V of PF is less equals to V of QF. That is, if we refine the partition, then this VPF will increase. Okay. So we will quickly see the proof. Okay, suppose P is this partition. So this x0 is A and xn is B, right? I am not mentioning it, but x0 is A and xn is B. Now P is this partition. Now Q is a refinement of P. So P is a subset of Q, right? Now we'll say that P1. So this is our AB. There is some x1, x2, xn, like xn minus 1, right? So Q is in between some, there must be a point, right? Here, maybe here, right? y1, y2, like this. So that P is contained in P. Sorry, P is contained in Q. So P is a proper subset of Q, right? So first take P1 to be some, so there must be some point in between this xk. So in P there is some xk and xk plus 1, right? So in between xk and xk plus 1 there may be some point in Q. So I am taking P1 adjoining only one point, right? Then we will increase the points to achieve this Q. First we will see this P1, only P1, right? So in first step P1 is, this is Q. Q is some A, x1, y1, like this, right? But for P1 we are taking only one point. No, this is xk minus 1, this is y, xk, this is xn, right? Is it clear till now? How I am choosing this P1? So in P1 I have taken only one point which is not in P but in Q, right? This y. So I have taken only the extra point y which belongs to Q but does not belongs to P, right? So we'll increase one by one point. So in P1 we have increased 1 point, then P2 will increase 1 point, and like this we will reach to Q, right? So for this step we will prove, and for the next it will be clear. So for P1 now, so first VPF is what? VPF is, and there will be this portion which is x k plus 1 minus f of xk plus, and then, right, and P1f except this term, all the terms will be there in P1f, right? So in P1f it will be f of x1 minus x0, and for this term it will be replaced by what? It will be replaced by fy minus f of xk, because there is a point in between x, oh sorry, this is xk and this is xk plus 1, right? So we are taking the difference between xk and xk plus 1 in P. So in P1 we will take fy to xk and fx plus 1, fxk plus 1 minus fy, right? So there will be two terms and all the other terms will be same, right? So the difference will be in these two terms, right? So this portion will be replaced by this sum. Now by triangular inequality you can clearly see f of xk plus 1 minus f of xk is less equals to f of xk plus 1 minus f minus fy plus f of y minus f of xk, right? By triangular inequality. And since all the terms are same in VPF and VP1F, so we will have VPF is less equals to VP1F, right? So we have increased 1 point, we have adjoined 1 point in P to get P1, and then we have found that VPF is less equals to VP1F. So this is P1. Now if we increase the point, then it will be less than VP2F, right? Now like this, if we increase, we will reach to VQF, right? Because P is less than, P is contained in Q, and we are reaching Q by adjoining one point at a time, right? So we have proved VPF is less than VQF, right? So if we refine a partition, then this sum VPF will increase. Okay, now we'll go to Riemann integral. So when we say a function is Riemann integrable, right? This we have to check. So what is Riemann integrable? So first we have to take a function which is bounded. Okay. So if be a bounded function on this closed interval AB. Now take a partition P be a partition of this closed AB. Okay. Now since F is bounded, so the supremum will exist. So let M be the supremum of fx when x belongs to this closed AB, right? And small f is infimum of fx when x belongs to this interval. Since it is bounded, these two will exist, right? This capital M and small m. Now in each subinterval, so this is AB and there is x1, x2, x3, some xr and xr minus 1 and xr is also there, right? Now for this subinterval, this xr minus 1 to xr, I am choosing this mr, which is supremum of fx when x belongs to this subinterval, this xr minus 1 to xr, right? And also this small mr is infimum of fx when x belongs to this subinterval, right? So clearly this small m is less equals to mr, right? Because it is infimum of fx when x belongs to the whole interval, and mr is a subinterval of this closed AB. So this will be bigger, and infimum is always greater than supremum mr, and also this will be less equals to capital M, because I am taking supremum. M is the supremum of the whole interval, so it is larger, right? So this relation is followed. Now we'll look at the sum, this m1 x1 minus x0, m2 of x2 minus x1, and mn of xn minus xn minus 1. So what is this sum, right? So this sum actually is called the upper Darboux sum, or the upper sum of f. The upper sum of f with respect to the partition P, because all these x1 xi's are coming from P. So with respect to this partition P, this is the upper sum of f. So actually this means if f is a function, so I am taking a continuous function here, but it may not be continuous, right? So what is m1? m1 is the supremum of fx from x0 to x1, right? So this is the partitions. Like this, right? Now m1 x1 minus x0 is, what does it denote? So m1 is what? m1 is supremum of fx in this partition. So supremum is what? In this partition, say x, this is x0. So in between x0 and x1, what is the supremum value? Supremum is actually this f of x1, right? This is the supremum of this in between x0 and x1. This is our m1, this point. So m1 into x1 minus x1. So x1 minus x0 is this portion, right? This interval, length of this interval. So it is actually the area of this rectangle, right? This is our m1, this point is m1, right? So m1 into x1 minus x0. So area of this region. And for the second one, x1 to x2, it is m2. m2 is what then? m2 is the supremum of fx in between x1 to x2. So supremum is this point. Oh no, supremum is this point, right? This peak. So it will be this portion, this one. This is the supremum, and like this we are going, right? So this is the upper bound, this is the upper sum of f. So actually the integration of f is the area bounded by this curve. This is f, so bounded by this curve is denoted by this Riemann integral when it is continuous. Now this sum this m1 of x1 minus x0 is the upper Darboux sum. This is the upper sum. So we'll approximate the area by this. We are approximating. Now for the next part, so now we'll take the small m. So what is this? Okay, now this is denoted by, this upper sum is denoted by UPF. Upper PF means the upper sum with respect to partition P of F, right? Now we'll take small m1 x1 minus x0 plus small m2 of x2 minus x1, and like this small n mn of xn minus 1. This is the lower Darboux sum, or the lower sum of F with respect to the partition P, and it is denoted by LPF, right? So in graph we have seen what is UPF, right? It is the sum of this block region, right? Area of these blocks. Now for m1 what we have to take mr. So first, what is m1? M1 is the infimum of fx in x0 to x1. So what is this? Is capital M1, right? Now M2 will be this point. So this point was M1, and this point will be small m1. So this point is small m1. So the region will be this x1 minus x1 x0 into small m1. So it will be area of this portion, right? I'm taking the dotted region. And for the next interval, what is the infimum of in this section, in this x1 minus x2? This is this point also, this point. So then it will be the area of this dotted region. It is small m2 into x2 minus x1, and will go on like this, right? So this is the meaning of these sums, these two sums. So this sum is UPF, which is the upper sum, and this m1 plus m1 of x1 minus x0, this is the lower sum of this f, right? This is LPF. Now for a single partition we are determining this, right? Now we'll vary this P on the family of all partitions, that is this PAB. Okay, so we'll take this set UPF where P belongs to AB. So we are varying P in the family of all partitions. So for all partitions we are taking this UPF, right? And we'll take LPF when P varies in this AB, right? So we have already seen from this this inequality what we get. M is less than MR. So we had M is less than MR, less equals to capital MR, and which is less equals to capital M, right? Now if we multiply by XR minus 1, and take the sum from 1 to n. So what is this? The second term? Second term is the sum of r equals to 1 to n mr xr minus 1. This is this number, right? So this is LPF. And the third term is what? Third is mr into sum of mr into xr minus 1. So this is actually this UPF, right? For a partition. For a partition P. So this means, and the first term is what? First term is if m is, so if we take m common, it will be xn minus x naught. So it will be m times b minus a, and the second term is LPF, third one is UPF, and the last is capital M into b minus a, right? So this we are getting. This LPF is less equals to UPF. So LPF and UPF both are bounded, right? Bounded above and below. So this set, this set UPF when P belongs to PAB, and LPF, the supremum and infimum will exist, right? Since they are bounded. So this means this set since it is bounded below, so infimum of this set, so infimum of this set exists, right? And let denote it by, and let infimum of this UPF where P belongs to the set of all partitions, we are denoting it by this ABF, right? And there is a small oh sorry, this is, since this is the upper, so, and supremum of this LPF will also exist since it is also a bounded set. So this set is bounded and this set is also bounded. So supremum, infimum both exist. So we are taking supremum of this and which will denote by this AB. This is the lower sum. Okay. So this you have to remember. Okay. So what we are doing is that, so we are taking in this graph, we are calculating UPF and LPF for each partitions, right? Now for UPF we are taking the infimum, right? What is the lowest upper bound, right? For UPF, see, for UPF we are taking the infimum, and from LPF we are taking the supremum, right? So we are approximating the area. So we'll say that F is a Riemann integrable when these two are equal. Okay, so we'll say that. So the definition is, so F is said to be Riemann integrable on this AB if these two happens. Okay, I will tell you. So this two, the lower sum and the upper. is equal. If these two are equal, then only f is said to be Riemann integrable. And when these two are equal, we'll denote it by a to b f. Only a to b f. Right? Okay. And the class of all Riemann integrable function, the class of all Riemann integrable function on closed AB is denoted by this RAB. So I'll say that f belongs to RAB means f is Riemann integrable on closed AB. Okay. So this is the notation. Okay, you will understand this thing when we'll see one example. Okay, so first I will take this example, the identity function. So fx is x when x belongs to AB. So we'll prove that f belongs to RAB. Means f is Riemann integrable on this closed interval AB. Okay, this we will prove. So this means we have to find this lower sum of f, this integral ABF and AB, this we have to find, and we have to check that these two are equal, right? So first we have to take a partition, the first thing. So let this be a partition of this closed AB, right? So we have taken a partition. Now what we have to find? We have to find this UPF and LPF, and then from this set, the set of all UPFs, we have to find the infimum of UPF and supremum of LPF, right? So for UPF, okay, what was UPF? So UPF was what? M1 of x1 minus x1, x0, right? This sum. And all this M1 was what? M1 was this supremum of f on the subintervals, right? So since our f is, see, our f is monotonically increasing, right? Right? So what is MR? MR is supremum of fx in xr minus 1 to xr, this interval, and since this is monotonically increasing, so supremum will be f of xr, right? So supremum is actually f of xr, since f is increasing and our function f is identity, so it is actually xr. Okay. Actually, I have to take this constant. For constant function, this will also be Riemann integrable, but we have to prove in different way. The sum here, you cannot see, say this is bounded for now. Okay, now first, for simplicity, let's take this function constant function, right? To understand this, we have to first prove some theorems for fx. The identity function is also Riemann integrable, but proving this you need some more theories. Okay, so first check this one, this constant function. So now f is constant, so mr is supremum is constant k, and infimum is also k, right? Now UPF is the upper sum, which is m1 of x1 minus x0 to mn of xn minus xn minus 1, and all these mi's are k, so it is k times this x1 minus x0 like this, so it will be b minus a, right? And again LPF is small m1 into x1 minus x0 to small mn of xn minus xn minus 1. So again small mi is also k, so it will also be k into b minus a. So this set UPF, where p belongs to this, so if we collect all the UPFs, it is only this set k into, this is singleton set. And similar thing for LPF, this is also equals to this set LPF. Right? So supremum of UPF, this set, and infimum of UPF, which is this one, is also k times b minus a, and a to b, the upper sum is also k times b minus a. So since these two are equal, so f is Riemann integrable. So f belongs to RAB. So constant function is Riemann integrable. Okay. Okay, now let's see next example. So this function if x is rational, it is 1. If it is irrational, it is 0. And x lies in, f is a function in 0, 1. So is it Riemann integrable or not? That we have to check. So take any partition. So P any partition of this 0, 1. Okay. Now what is MR? MR is supremum of fx in this interval xr minus 1 to xr, in a sub-interval, right? So this is our AB, and there is some xr minus 1, there is xr. Since it is an interval, so it contains infinitely many rational and irrationals, right? So in this interval, closed interval xr minus 1 and xr, there are infinitely many rational and irrational points, and in irrational points the function gives the value 0, and in rational it gives the value 1. So the supremum in this interval is 1, right? In each interval the supremum has to be 1 and the infimum has to be 0, right? Because each interval contains rational and irrational numbers, right? So MR is always 1 and small mr is which is the infimum, this is 0, right? This is clear, right? So what is UPF now? So UPF is m1 of x1 minus x0 mn time xn minus xn minus 1. Right. Now all these capital MI's are 1. Right. So this implies, since all of this is 1, so the remaining will be, so it will become this one, xn minus xn minus 1. Right. And this will cancel out. So we'll have xn minus x0, which is b minus a. Oh sorry, since we have taken the interval close 0 1, so this is b is 1 and a is 0, so it is 1, right? Because b minus a is 1, right? The interval is close 0 1. So UPF is 1, and what is LPF? Small n m1 of this. Right. Now all these small mi's are 0, so it is 0. So LPF is 0. Now what is this supremum of this LPF? This is also 0. Supremum of LPF is this one, right? This is the supremum of this LPF. We have denoted, which is 0, and this number, this is infimum of this UPFs, which is 1, this constant 1 singleton, this set is singleton, so infimum is 1, right? So these two are not equal. So this implies f is not Riemann integrable. So this means f does not belongs to R01, means f is not Riemann integrable. This means f is not Riemann integrable on 0 1, right? So this function is not integrable, Riemann integrable, right? Now we'll prove that fx equals to x is Riemann integrable, but for that thing we have to prove some theorems. I think it will not be covered in this class. So okay, so I'll end it by defining the refinement, how the refinement works in this Riemann integration. So refinement of a partition. So I have already defined what is partition and what is refinement of a partition. Right. So let f be bounded and P is a partition of this AB, right? Now if Q is a refinement, Q be a refinement of P, then so we have UPF and LPF for the partition P of this function f, right? Now how it is related to UQF? So then we'll have that. So and LPF is less equals to LQF. So if we do the refinement, then the upper sum U will decrease and the lower sum will increase, right? So this is basic theorems. You can check any book for this references, right? Okay, I will write the books. So the books are, so the first one is, this is book by S.K. Mappa, Introduction to, both the name are same. Introduction to Real Analysis by S.K. Mappa. And the same name, Introduction to Real Analysis by Bartley. So these two are very basic books. Okay. So for starting, they are very good book. And if you are already seen this book, then you can check the book by Rudin. Okay. So now if you have any doubt, then you can ask from this session. So in the next day we'll first prove some lemmas, then we will prove that the identity function fx equals to x will be Riemann integrable. Okay, so if you don't have any doubt, then I'll end this session. Okay, then. Okay, so good night then.